All right, let's talk about something we use every single second of our digital lives, but maybe don't think about too much. Computer networks. Every time you send a message or watch a video, you're tapping into this hidden global architecture. Today, we're going to pull back the curtain and look at the fundamental rules and blueprints of that digital world.
I mean, it really does feel like magic, doesn't it? You hit send, and poof, your message is on the other side of the planet. But it's not magic. Behind that simple action is an incredible, invisible system of rules and pathways that makes it all happen. So, here's our game plan. We're going to build this thing from the ground up. First, we'll cover the grammar that devices use to talk to each other. Then, we'll explore the different city plans or blueprints for connecting them. After that, we'll look at the actual physical highways that data travels on. And finally, we'll see how it all comes together to create the connected world we live in. Okay, let's start with the absolute basics. Before any data can go anywhere, every device involved has to agree on how to talk to each other. It's not negotiable.
And you know, this idea is totally universal. It doesn't matter if you're sending a smoke signal or streaming a 4K movie. You always have a sender, a receiver, and some kind of path between them. In our world, that's your laptop sending an email to your friend's phone, and the channel? That's the internet itself.
So how do devices know how to talk? Well, they use something called protocols. You can think of protocols as a shared language, and even good manners. They make sure that when one device speaks, the other one understands not just the words, but the timing, the context, and, when it's their turn to reply.
And these protocols get into the nitty-gritty. I mean, they manage everything from the size of the message to its format, how it's encoded, the timing of it all, basically making sure the message gets to where it's going perfectly intact and, actually readable. Okay, so once devices agree on the rules of the conversation, the next big question is, how are they all physically connected? This is where we get into network blueprints, or what the pros call topologies.
The best way to think about this is like city planning, right? A city can have a rigid grid system, or it can have winding country roads, or maybe a hub-and-spoke model where suburbs all connect to a downtown core. Each layout totally changes how traffic flows, and networks are exactly the same way.
One of the earliest blueprints was called the bus topology. Super simple idea. You have one main cable, the bus, and every single device just plugs right into it. But that simplicity was also its biggest problem. If that one cable went down, the whole network was toast.
Then you had the ring topology. Here, data literally travels in a circle, passed from one device to the next, and each device kind of helps boost the signal as it goes along. But just like the bus, one break in that chain could bring the entire network to a standstill.
And that brings us to the star topology, which is pretty much the design you'll find in most homes and offices today. As you can see, every device gets its own dedicated line to a central controller, like a hub or a switch. That controller acts like a traffic cop. If your computer wants to send a file to the printer, it sends it to the hub first, and the hub relays it to the printer. This setup has some huge perks. It's way cheaper than other complex designs, and it's easy to manage. If one computer's cable fails, it only affects that one computer, not everyone else. But, and this is a big but, the whole network depends completely on that one central hub. If the hub dies, the entire system is dead in the water.
Okay, so we've got our layouts, our digital city plans. But inside that city, how are the messages actually delivered? Is it like a private letter to one house, a flyer dropped in every single mailbox, or maybe an announcement just for one specific neighborhood? Let's break down the three main ways data gets addressed.
The most common method by far is unicast. This is a direct one-to-one conversation. Think of it just like sending a private text message from your phone to one specific friend. The data is addressed from a single source to a single destination. Simple. At the complete other end of the spectrum, you've got broadcast. This is the equivalent of shouting through a megaphone. One device sends out a message, and every single other device on the local network hears it. It's useful for big announcements, like a computer trying to find a service on the network.
And finally, we have this really clever middle ground called multicast. This is a one-to-a-group transmission. The message isn't for everybody, just for those who've specifically subscribed or shown interest. The perfect example is streaming a live video. The server sends out just one stream, and only the devices that have opted in actually receive it. It's way more efficient than sending a separate individual stream to every single viewer.
So we have the rules, we have the blueprints, and we have the delivery methods. But what is the data actually traveling on? Let's get physical and look at the cables and waves that make up the highways of the internet.
So at the most basic level, networks are either wired or wireless.
Wired networks, they use actual physical cables. They're fast, they're stable, they're secure. Wireless, like your Wi-Fi, uses radio waves. Not as stable maybe, but it gives us that amazing freedom to connect without being chained to a wall.
Let's actually peek inside one of these physical pathways. This right here is a coaxial cable, probably the same kind that brings cable internet to your house. You can see all the layers. That copper wire in the middle carries the signal, and it's wrapped in insulation and shielding to keep out any interference.
And there's a whole family of these things, each with its own job. You've got your standard twisted pair cables. That's the workhorse of most office networks. You've got the coaxial cable we just saw. And then there's the king, fiber optic cable. It uses pulses of light to send data at mind-blowing speeds over huge distances. It's literally the backbone of the entire global internet.
All right, we've covered the rules, the blueprints, and the physical highways. So for our last section, let's put it all together and see how these pieces create the digital world that we absolutely depend on every single day.
Seriously, every single time you video chat with family or work with a coworker on a shared document or just stream a movie, you're relying on this incredible architecture. The protocols, the star topology in your house, the fiber optic cables running under the ocean, it's all working together in this seamless, invisible dance.
And the impact is just staggering. This is what powers our instant messaging and social media. It's what changes how we work, letting us access the office from literally anywhere. And it has completely revolutionized education, with online learning breaking down geographical barriers for students all over the world.
And this isn't just about the tech, right? It's about people. As one of the core texts on this subject points out, this instant communication creates global communities. It lets us connect with people we'd never otherwise meet, totally independent of where we are or what time it is.
So, from those simple bus layouts to the complex, tangled global network we have today, these digital blueprints have been constantly changing and evolving. It really leaves us with a fascinating question to chew on. As our need for more speed, more connectivity, and more intelligence just keeps growing, what's the next blueprint going to look like? Thanks for tuning in.